Please see the covered thing in presentation. So this chapter discusses the basic principles behind the use of electromagnetism in sensing. As I already told you, the basic element which is involved in electromagnetism for sensing is inductor. So we need to see its fundamental properties. The first one, the voltage governing equation for inductor is minus L di by dt. That is, it resists the changes in current. The second fundamental property of inductor is about its complex resistance, which is given by j omega L. Continuation of the properties of inductor. If suppose we wanted to know how big the inductor is, we can use this formula U0 N square A divided by its length. This is useful in order to find out the excitation frequency of the AC signal. The next, we will see the creation of magnetic field due to the electric effect. This is actually discovered by Mr. Oster. According to him, a magnetic field is created in the surrounding of a current carrying conductor. For the case of simple wire, it is given by this relation: V is equal to mu naught I divided by 2 pi R. Now, I told you the surrounding magnetic field, which when act on the movement of charges, it influences some force on it, and that is called as Lorentz force. And the magnitude of this is given by QV into B. Up to this I have covered. Now from now, I will cover on the presentation. So everybody got to know about the fundamentals of the inductor, which is actually playing the key role in the electromagnetism principle, which we are using here in this particular case for sensing. So we have seen this thing, Faraday's law. Once more I am repeating, it is given by this relation minus d phi by dt. Now we are coming to sensor application. The first application, what we will do is, what we will cover is the measurement of velocity of a coil. Measurement of velocity of a coil. Suppose we have a setup like this. A magnet is available over here. Okay, like this magnet is available, which is creating a magnetic field in this particular area. Only in this particular area. So the length is suppose x, and this is W, width. Then the flux value is simply nothing but the area. Multiply by how much is the magnetic field available in this particular area. So the area will be, in this particular case, is W into X. So the flux value will be W X into B. Now if we apply Faraday's law on this flux, then according to Faraday's law, the V value is given by minus d phi by dt. So V is constant minus d by dt of Wxb. If we write, this quantity is constant, this quantity is also constant. So we can write Wb into d by dt of dx. So the meaning of this thing is, suppose we have a coil. We have a coil, okay? This is suppose coil moving in and going out, moving in and going out. Its velocity or its rate of change of the dx can be determined by determining the voltage produced in the inductance. That is, you see, V is directly proportional to dx by dt, which is nothing but velocity of coil. I repeat this thing. The first application is measurement of velocity of a coil with the help of magnetic sensor. The setup available over here is, suppose we have a permanent magnet whose magnetic field is available only in its confined area, whose length is x and breadth is w. So we all know that the flux is given by area into B. Area is W into X multiplied by B. So if we apply the voltage equation on this phi, we know that Faraday's law is given by this relation V is equal to minus d phi by dt. So in place of phi, we can write Wx into B. So W and B are a constant. So only X will be applied on this differential equation. So we will get finally V is equal to minus W dx by dt. So it means that V is directly proportional to dx by dt, which is nothing but velocity of coil. From presentation, magnetic sensor. It is an example of Faraday's law of electromagnetic induction. Make a note of this. Okay, if you want, you can have things from ebook, or if you want, you can make a note from the presentation, whichever left. The first thing you can write, the principle of this particular application is, it is based on FL, Faraday's law of induction. So maybe this is drawn to scale, or you can find this type of circuit, or sorry, the sketch or the diagram from the ebook. You see, I try to make the same sketch because from the point of view of understanding, if I do some work on whiteboard, that will be more understandable rather than showing on the presentation. So I will be trying to do both one after the other. So this only I have shown you. Suppose we have a setup, a coil whose velocity we want to determine. In order to do the determination of this thing, what we thought of doing is, we thought of surrounding a magnet around this. Okay, so this movement going in and coming out of this coil can be determined with the help of our Faraday's law. So this coil is actually containing a fixed magnet. Its length is x and its breadth is w, and its magnetic field is suppose B. So the induced voltage V can give us the relation between the velocity of the coil, which we actually wanted to find out. Here the text is written, which I had taken simply from the textbook. So the magnetic field is confined. The first assumption we need to make is this one. The magnetic field is confined to the region between the pole faces and is essentially zero elsewhere. Otherwise, we will get error. If suppose we take the effect of W, we take the effect of X, in which magnetic field is not available, zero magnetic field is available, then in that case we will get definitely error in the measurement. That we need to keep in mind, and we also need to write in the text who were asked this question. This is the assumption. What is the assumption? The dimension of magnet should cover uniform magnetic field effect, and it should not cover zero magnetic field effect. Okay, then the magnetic flux through the loop in this situation is simply the A multiplied by the B, which I have shown you just now. So this also I have shown you. So we can write phi is equal to VW into X, and the induced voltage we can write like this, minus VW into dx by dt. Hence we can say that it is actually a motion detector where dx by dt is velocity of coil. Either we can call it to be velocity finder, or we can call it to be motion detector. Whether any movement of coil is coming or not, If suppose our requirement is just to find out whether any movement of coil is there or not, it is coming in or not, it is coming in or not. In that case also, in that case it will be a digital or a discrete sensor. Otherwise, if you are finding velocity of coil, then it is analog sensor. So sometimes this type of motion detector is motion detector. Okay, please also make a note of it. Apart from finding velocity, it can also be used as motion detector. Please add a point. It can also be used as motion detector. It can also be used as motion detector. Now I am asking a question. Sincerely answer if you know. Can you tell an application in which motion detection is important? For that, we can use this motion detecting concept. But this may not be the appropriate solution for that particular problem. Okay? First of all, let me make you this particular application clear. Motion detection is very important requirement in most of our in and around applications. Okay. Second point. Can we use this motion detector for lighting application? Is second question. Yeah, anybody know this answer? This particular setup, इधर देखा और से देखो. This particular setup need the object whose motion we are trying to detect should be a conductor. Agree or not? Tell me. I repeat. The object whose motion we are trying to determine must be made up of metallic object, or it must be a conducting element. अब तो इंसान conductor है क्या? Is it made up of metal exclusively? Then we cannot use. Then something else, some other concept should be used in order to determine the movement or the motion of humans or animals. Okay, metallic object motion can be easily determined in this particular setup. Okay, so if it is clear to everybody, we will move to next topic. Please note down the last point. I think you have not taken this thing, and add this also. This particular setup is an example of motion detection, where this I already told you. This only please make a note in your notebook. Let us see this motion detection application for a special purpose geophone. Same fundamental principle. If a question comes in the examination, explain about geophone. Then you need to start from that Faraday's law principle for making a magnetic sensor. Give that relation, show that setup, come to a conclusion that V is given by minus WB into dx by dt. After that, you can give this particular point, which make it confirm that that particular setup can be called as geophone. So what is geophone? In this, a coil measures a differential voltage, which is what just now we are talking about, whenever a spring supported magnet moves. So here a magnet which is spring supported gets displaced, and this displacement we actually wanted to find out, which is called as geophone. I repeat, there is a magnet, okay, which is spring supported. Spring supported means it is actually oscillating when force is applied, okay, and come back to its original position when force release. So this magnet will get displaced, okay, when a particular force is applied onto it. That we can determine with the help of this type of formula, minus dw into dx by dt. So coil, that is inductor. Measures a differential voltage whenever a spring supported magnet moves. Okay, it is commonly used in oil exploration business, that is in our refineries, petroleum industries, for the sake of detecting explosive charges. Okay, hidden explosive charges, to map underground resources deposited. So in the refinery, if any explosive charges are available, that can be determined with the help of geophone kind of setup. Okay, this diagram is available in text. You can also draw this thing, or I am here. You can make a note of it. Or I will be sharing the video recording of this also. Anyhow, please make a note because still time is there. It's clear. Please make a note of it. So in general, the geophone is nothing but a motion detector, which is used in refineries. The meaning of plus 1 millimeter and minus 1 millimeter is it can go in plus 1 millimeter to minus 1 millimeter displacement in and out. Okay, so this is enough for today's class.